All right. Today let's look at how to do an airbag simulation inside LS-Dyna, and it's not just going to be about an automotive applications. I think airbag modeling can be used for a lot of different things that doesn't really have much to do with cars, which is what I like to sort of demonstrate today. I have some example video. One is for like a balloon catheter. One is for an airbag inflation, which I will demonstrate in a second. Okay, basic agenda. I'm gonna look at the basic principle behind airbag modeling. It's pretty simple, just a basic control volume. And then we'll have a few example. We're gonna dive into. I prepare like 3 to 4 different examples. Some of them I borrow from my past videos. And then we're gonna look at each of them to understand how they work and how they're used, while how they're different. Overall, I think it's a relatively pretty simple to implement into a real model, and it's very very useful for a lot of different reasons. And I'd like to show some example models that can be translated to a much bigger application model very easily. All right, so overview. Airbag model are basically these long parameter CV model, control volume models. Right? We calculate the volume of the airbag based on the FE model, and then the pressure is then applied to the control volume inside the wall based on a various factors. And then you can scale this pressure, you can offset this pressure, based on the initial the core key card in any airbag model, and then the thermodynamic state, thermodynamic relations of the airbag, volume, temperature, and density of the gas, and so on and so forth, defines how much pressure is then applied to the wall. So depending on the situation and application, depends on what you know. Like say for example, if you know mass flow rate, then you can define mass flow rate as an airbag model. If all you want is to define a internal pressure, you can define internal pressure. If you wanted to model the airbag with a different kind of gas for whatever reason, you can do that as well, right? So they give you the flexibility to model airbags by defining whatever you want to define as an input parameter, right? Because the thermodynamic state in the end is going to be the same. You have your pressure, your volume, and all the other variables, and that together help you define the behavior of the airbag. Okay, and there are sort of a few general approaches. We are only going to talk about the simplest one, which is control volume. This is the most easiest to use and the least complicated. You can also approach this with an ALE or a particle method. ALE and particle method, just like you can do with any other multi-physics problem that use ALE or use particles, except in this case, incorporate that into the airbag. This is where you instead of model it as a long parameter, CV, you model it with actual particles and actual elements for the gas inside an airbag, which is way more complicated than I will probably ever use in non-auto situations, which is why I like to focus on the control volume approach. Okay, there are about 5 to 6 different examples, right? I'm gonna go over I think 4 of them today. The Wonevsky is slightly more involved. The adiabatic gas model, I just don't have any good example about it, so I'm not using it. I can't really think of a reason I want to use it right now, at least. So I'm not using it. I'm not giving an example, but I'm gonna focus on the first 4 with some actual example in this video this week. Okay. All right, let's look at the very basic one, simple pressure volume. So this is the one I've actually used before. So this is the one that I used in the past to model essentially about impacting a wall like this. So what this model does is that it starts with essentially some initial pressure, which is defined in the tabulated data here. And then based on the change in the pressure and volume, it defines how much the pressure increases when you decrease the volume, right? So you have some internal pressure at this state. It's gonna hit the wall. When it hits the wall, internal pressure is not enough to prevent the ball from deflating. So the ball is gonna deflate. But as it deflates, the pressure is gonna go up, right? And that's how you have a ball with this kind of bouncy behavior and some initial compression behavior. Is because of this. So this is very similar to like a ball or a tire, right? So if you want to model something like a bike tire or a car tire, whatever it is, if you just want to model something that's internally pressurized, this is a very useful thing to do, right? What's in the coefficient here is going to be your inflation pressure at t equal to 0, and then the pressure can change based on the change in volume. So the basic principle is essentially this, right? Like I said earlier, you define your initial pressure. So if you can imagine here, relative to volume is current over initial. If current is same as initial, which is at t equal to 0, that's the case, then relative volume is 1. Therefore, your pressure is just your Cn, assuming your beta, your scale factor is 1, right? So pressure is essentially your Cn number. The Cn number is what's in the tabulated data, okay? But as your volume changes, the relative volume is going to change, which is going to drive a different pressure value. And that's in essence what a simple pressure volume airbag is. Very useful. Also very easy to implement. Okay, extremely easy to implement. And inside Workbench, all you have to do, you can see in this model right here, I have a rigid wall, right, which is defined from the coordinate system. Make sure your z-axis is pointing towards the bodies, right? And then you have your airbag model. The airbag model is scoping to a ball, which has an airbag, and then this airbag model is going to basically call on these parameters. That's all you have to do. Then you add an initial velocity, or drop height in this case, and you're done. Very easy. You can see, right? It's a very easy thing to implement. Nothing special to it. Okay, but also very useful. All right, let's look at the next one. Next one is called airbag load curve. So this is the one where we're essentially defining pressure directly inside the airbag, right? So for example, if you want to start with a deflated airbag, and then you want to inflate it to some pressure, right? Let's say for that's the case, and then you want that inflated airbag to push against something else, for example, which by the way happens all the time in testing. People want to apply a external pressure to a body, they just use an airbag to do so, right? It's a very convenient way to apply that kind of pressure, and then it sort of conforms to the surface as well. So the way you do that is basically you use this airbag load curve, and you can also actually use inside Workbench. You actually have the airbag functionalities that you can just formulation change the load curve, and all you're doing here is you can set D to 0, by the way. You can define the tabular data. The tabular data is basically your pressure, your internal pressure as a function of time. So when you have something like this, so that what happens is that you can see this right here is that I have T equal to 0, I have the airbag mostly deflated, right? And then as the pressure ramps up, you can see the airbag goes up like that. So it's a pretty convenient way to essentially directly define an internal pressure, but you do it from inside a control volume that's deflated, right? That's when it's really useful, because you want to ramp the pressure up from not some, because you remember in the simple pressure volume you have some internal pressure at T equal to 0. In this case you have no internal pressure at T equal to 0, so you want to start with a deflated airbag, not with some random shape that somehow it stays there. It doesn't really stay there if you think about it, right? So you want to start this with some deflated shape, and that allows you to use this curve much more likely. Remember, right, in this case this thing starts at 0, whereas in this case this thing does not start at, this thing starts at a Cn number. Okay, and that's the real difference between airbag load curve and simple pressure volume, is that the nature of application is slightly different. You don't want to use this for a simple on a ball, because the ball will have no internal pressure at start. That wouldn't make any sense. Okay, next one. Okay, let me demonstrate this real quick. So the interesting thing about this, there's one question that one will ask is, how do you generate a deflated airbag at T equal to 0, right? So the way you do that is actually exceedingly simple. And then this is my own method. I'm sure in the auto industry where people crash cars all the time, they might have a different idea. But for me, this is an extremely simple thing. You see, I have two sheets that's separated by some gap. That gap right there is very small, right? That represents a deflated shaped gap. And if you can imagine, if I were to mesh this, you're just gonna have two shell bodies, right? Shell meshes, shell elements across the board. You can see this in this case. You see how the edges are linked together. All I did was because I no merged them, right? So you have generated no merge across the edges of the two sheet bodies, and I set the tolerance to be the gap or greater than the gap. And what you have is a set of no merge across it, and then across the edges of the airbag, essentially knitting it together as if they're knitted together. And in this case, you can sort of see, because they're knitted together, you have essentially inside you have some volume, but on the very outside it's not knit together. And then the rest of it is exactly how you expect. You have an airbag which is going to apply the pressure. Okay, and that's how you use a low curve airbag. In my opinion, extremely useful as well for just using an airbag based pressure boundary conditions. Very useful. Okay, let's look at a simple airbag model. So simple airbag model is going to be slightly different from the other ones, in the sense that we're no longer applying a pressure directly. What we're doing here is using the gamma law of equation of state to basically define mass flow rate, to indirectly define pressure, right? So based on the constant heats at different volume, at constant volume and constant temperatures, right? So you can sort of define what happens to the gas based on its also initial temperature and density and so on and so forth. Right? So based on these parameters right here, you can define the thermodynamic state, and then by defining a mass flow rate, you can essentially define how the pressure ramps up So this is only useful if you're actually sort of designing a airbag type of device, right? And you want to sort of calculate, you know exactly how much air you're pumping into that control volume, and then you want to figure out based on the amount of air you're pumping into it, is it gonna generate the shape you're looking for, right? So you're no longer just defining a pressure, because in process you can generate a pressure. In process or in design, you're generating an airflow into that control volume. So one of the best examples that I can think of is a balloon catheter. So if you can think about the nature of a balloon catheter, right? They usually have a syringe that push against the balloon catheter, and it will inflate the balloon. So in that case, you know exactly how much air you're pumping into the balloon to generate the balloon. So you can actually calculate based on the thickness of the material, the nature of the material, stiffness of the material. Are you able to inflate a balloon without it popping, or can you inflate the balloon to the right amount of size? So in this case, I have two balloons that's being inflated by the airbag model. And in this case, I'm defining a arbitrary mass flow rate into it, right? And that's how I know how much I'm pumping this balloon up. And that's a very direct way to define the problem. If you know how much air you're pumping into it, you know what to do. So in this case, the problem is relatively simple. Oh, I did not have it saved. Oops. So let me open that up. Which I think is inside, not this one, and this one. Give it a second. All right, while it's loading up, I'm just going to, oh, actually, it already popped up. That's pretty fast. No, it's not, actually. Sorry. There it is. Okay. Just want to show you real quick how this is done. Right, in this case, I still have a deflated airbag in the beginning, right? I don't have anything. So what I did was the same thing as the last video I showed you. I knit the edge together, and then I tie the bottom edge to the tubing. And then what you have inside here are basically these airbag 1 and airbag 2, right? These airbag are then get inflated based on some specific mass flow rate that I'm defining, and that's all I'm doing. Okay, very simple. Because I did that, you can sort of see I can generate essentially the airbag shape that I'm looking for. Of course, depending on the length, the height, and all that, and then the material, you can inflate this to a different amount. In this case, I only inflate this much. Anymore, my material model, I'm making up a material model, so it's not exactly working, but you can sort of see this is a decent common type of shape you will see inside a balloon catheter, for example. All right, last one, which is a one I've actually already shared before, so I won't go too much into it. But basically, the simple linear fluid is for hydrofoaming. So this is an airbag model that can be based on both a mass flow rate and a direct pressure. So if you have an airbag model that you want to define based on either the mass flow rate or a direct pressure indications, you can do so. So it give you both access to both capabilities, and it's very useful for hydrofoaming because in this case you're actually defining the bulk response, the bulk modulus, and the density of the liquid or the gas inside the tubing, right? Because that helps you, that combine that with the mass flow rate, helps you define how much pressure you're applying to the airbag, to the control volume to generate the internal pressure, right? And it is a function of the mass flow rate. So depending on how quickly you're ramping up the mass flow, you have a different pressure gradient or pressure ramping up in that process. So this is something that I've shown before. So what you have here is starting with this shape, then you're applying in this case I apply a direct pressure, but you can also apply a mass flow and define the proper bulk modulus and the density of the gas of the fluids, and that will allow you to apply a pressure into all the internal surfaces, generate a hydrofoaming process. So imagine you actually have fluid pressure inside this tubing right now, right? And that's a very good way to model at what thermodynamic state of my fluids can I generate the correct amount of hydroform shape. So it's a way to use the hydroforming process parameters to directly define the responses or directly model the responses. Okay? And these are the parameters, and these are the basic equation. I'm not going to go into it, but it's basically, you can sort of imagine they're all relatively similar, right? So Ft, Gt, and Hp are these three parameters: input flow, output flow, either as a function of time or as a function of pressure, right? So you're basically defining a analytical solution inside the tubing, inside the airbag to calculate the control volumes and its responses. And that is the end of the presentations. I hope you find this helpful. Again, 4 different airbags are all extremely useful. Thank you.